Welcome to my Friday Swift Code Challenge. This challenge is part of a series designed to help you learn and practice Swift programming. This week's challenge is a bit of an odd one, but in a good way. It's called the Sum of Odd Numbers Challenge, and it goes like this. Create a function that takes in an array of integers and returns the sum of all odd numbers in the array. For example, if your input array is the following -2, 1, 3, 5, your function should return 9 since the odd numbers are 1, 3, and 5. And 1 plus 3 plus 5 is, well, 9. Remember, your function should work with any array of integers, not just the example above. The easiest way to check if a number is odd is to use the modulo operator, which returns the remainder of a division operation. If a number n is evenly divisible by 2, n mod 2 will evaluate to 0. On the other hand, if n is not evenly divisible by 2, n mod 2 will evaluate to 1, meaning that the number is odd. For example, 3 mod 2 is 1 because 3 divided by 2 has a remainder of 1. But 4 mod 2 is 0 since the remainder of 4 divided by 2 is 0. You can use this knowledge to finish the challenge. There are also other, more sophisticated ways to check if a number is odd. I'll show you one such method in my solution, but first, try to come up with a solution on your own. Pause the video and give it a try. And when you're ready, we'll walk through my solution. Good luck! Welcome back! How did you do? Now, let me show you my solution. First, I'll declare a function and name it SumOdd. It takes in an array of integers as a parameter and returns an integer. I'll declare a new variable called result and initialize it to 0. This represents the final sum that will be returned. Now I'll use a for loop to iterate through the numbers in the array. For each number, I'll use the modulo operator to check if it's odd. If the result is 1, that means the number is odd and I'll add it to the running total. When the for loop is finished, I'll return the result. And that's it. Let's try it out. If I input the array of numbers 1, 2, 3, the output should be 4 since we've got two odd numbers, 1 and 3, that add up to 4. Let's see if that's the case. The output is 4, just as we expected. And if I input the array of numbers -2, 1, 3, 5, 7, the function should return 16 because the sum of the odd numbers is 1 plus 3 plus 5 plus 7, which is 16. Awesome! Now, there's another way to check if a number is odd that's a bit more sophisticated. Instead of using the modulo operator, we can use the bitwise XOR operator. The main idea behind this approach is that the last bit of an odd number is always 1, while the last bit of an even number, 0. For example, if we take the number 12, its binary representation is 1100. 12 is an even number, so its last bit is 0. On the other hand, if we pick an odd number, say 11, and check its binary representation, which is 1011, we'll see that the last bit is 1. Now comes the interesting part. If we XOR a number by 1, its last bit will be flipped. If the last bit is set, which is the case for odd numbers, XOR by 1 will turn the last bit to 0, decreasing the number by 1. However, if the last bit is not set, XOR by 1 will set it to 1. Thus, it increments the number. So, if we XOR an odd number by 1, the result will be equal to its decremented value. I'll show you what I mean through an example. Take the number 3. Its binary representation is 0011, or simply 11. 3 XOR 1 equals 2, and as we can see, the result is indeed equal to 3 decremented by 1. Now let's see how we can use this in our code. I'll change the condition if n modulo 2 equals 1 to if n XOR 1 equals n minus 1. And the function should work exactly the same. Yep, same results. There you have it. These were two different ways of checking if a number is odd. But why do we need to know this? The answer: performance. The bitwise operators are actually faster than the normal arithmetic operators like the modulo operator. So if you need to optimize your code for performance, then using bitwise operators would be a good idea. Although it doesn't really make a difference in this case, imagine if we had to sum up 1,000,000 numbers. In this case, the difference in performance would be quite significant. And by the way, if you're interested in learning more about code optimization, algorithms, and data structures, I suggest you check out my course on Udemy, Introduction to Algorithms and Data Structures in Swift 5. Welcome to another Friday Swift Code Challenge. Today, we'll implement an algorithm in Swift that solves a 2x2 system of linear equations using Cramer's rule. First, let me give you a little bit of background. A 2x2 system of linear equations is a system with two equations and two unknowns like this. Now, one way to solve this system is by using substitution. We can solve for one variable in terms of the other and then plug that into the other equation. So I'll show you how to do that. First, let's solve for x in terms of y. Now we can plug this back into the other equation and solve for y. And now that we have y, we can plug it back into the first equation to solve for x. So the solution to our system is x2, y1. Although this approach is simple, it can become tedious for larger systems. Imagine a 4x4 system. We would have to solve for each variable in terms of the other three, and then plug it back into the other equations. Not the most fun thing to do, and definitely not efficient in terms of time or code. This is where Cramer's rule comes in to save the day. It's a much simpler and faster way to solve systems of equations that have the same number of equations as variables, and it relies on determinants. A determinant is a value that can be computed from the elements of a square matrix. Okay, what's a matrix, you ask? A matrix is just a two-dimensional array of numbers written in the following form. Given a 2x2 matrix, A1, B1, A2, B2, we can calculate its determinant using the following formula. A1 times B2 minus B1 times A2. For our 2x2 matrix, this gives us 2 times minus 5 minus 3 times 4, which is minus 22. Cramer's rule states that the solution for a 2x2 system of linear equations is given by x equals determinant ax over determinant a, and y equals determinant ay over determinant a, where a is the coefficient matrix and ax and ay are the matrices formed by replacing the coefficients of x and y with the constants c1 and c2 respectively. So for our system, A would be A1, B1, A2, B2, and AX and AY would be C1, B1, C2, B2, and A1, C1, A2, C2 respectively. Now, to find the solutions for x and y, we need to calculate the determinant of a, ax, and ay. So for our system, we have determinant a equals a1 times b2 minus b1 times a2, and determinant ax equals c1 times b2 minus b1 times c2, and determinant ay is a1 times c2 minus C1 times A2. And to calculate x and y, we just divide these by determinant A. Note that if the determinant of A is 0, then the system of equations has no solution. Now that we know how to solve a 2x2 system using Cramer's rule, let's put it into practice with the code challenge. The challenge is to write a function that takes in the coefficients of the variables and the constants. The function should then return a tuple containing the solutions for x and y. For example, if we have the following system, we should call our function like this: solve a1 2, b1 3, c1 7, a2 4, b2 minus 5, and c2 3. And it should return the tuple 2 and 1. So go ahead and try to solve this challenge on your own. I'll be back in a bit with the solution. Glad you're back. Let's take a look at my solution to this challenge. First, I'll define a structure to describe a 2x2 matrix with elements of type float. Here, the numbers represent the positions of the elements in the matrix. So M11 is the element in the first row, first column, and M21 is the element in the second row, first column. You get the idea. I'll go ahead and define a function to calculate the determinant of a 2x2 matrix. It takes in a matrix 2x2 instance and returns a float. And we'll use the well-known formula, matrix M11 times matrix M22 minus matrix M12 times matrix M21. With these two pieces in place, I can now write my function to solve a 2x2 system of linear equations. Solve, and then I provide the coefficients a1, b1, the constant c1, and then a2, b2, and finally c2. And the returned value is a tuple x of type float and y of type float 2. I'll make this return type optional because, as you might remember, if the determinant of A is 0, we won't have an actual solution. Next, I create a constant for matrix A of type matrix 2x2, and I'll initialize it using the input parameters. So for M11, A1, M12 should be B1, M21 is A2, and M22 is B2. And now let's calculate the determinant. For A is, and I call our new function determinant and pass in the matrix A. If this determinant is 0, then the system of linear equations has no solution. In this case, I'll just return nil from my function. Otherwise, I'll create matrices AX and AY, which are simply A with the first and the second column replaced by the constants C1 and C2 respectively. So let matrix AX equals matrix 2x2, and M11 should be the constant C1, M12 B1, M21 here I'll pass in the constant C2, and M22 is B2. And let matrix AY equals matrix 2x2, and for M11 we have A1, for M12 C1 we now replace the second column, M21 is A2, and M22 is C2. And now we can calculate the determinants. Let determinant of AX equals determinant, and I pass in matrix AX, and let determinant AY equals determinant matrix AY. Finally, I can calculate x and y using Cramer's rule and return them as a tuple. Let x equals determinant AX over determinant A, and let y equals determinant AY over determinant A. Finally, I return the tuple with x and y. And that's it. That's all there is to solve a 2x2 system of linear equations using Cramer's rule. Let's try it out with our original example. As you can see, the function works as expected and returns the tuple 2.0, 1.0. Cramer's rule is a great way to solve systems of linear equations, and it can be especially helpful when you have a large number of unknowns. How did you do? Did you come up with a similar solution, or did you take a different approach? I'd love to hear about it in the comments. And if all this talk about algorithms and data structures has gotten you interested in learning more, I recommend checking out my course Algorithms and Data Structures in Swift 5. Link in the description below. In the previous episode of the Friday Swift Code Challenge series, we solved a 2x2 system of linear equations using Cramer's rule. This week, we're gonna build a ring progress bar in SwiftUI. A ring progress bar is a type of circular progress indicator similar to the one you might see on your Apple Watch. It's composed of rings that fill up as the progress increases. Here's what our final ring progress bar will look like. As you can see, it consists of a ring that starts out empty and gradually fills up as the progress increases. To build this ring progress bar, we're gonna need a few things. First, we'll need a way to render a circle. That's pretty easy to do in SwiftUI. We can just use the built-in circle shape. Second, we'll need a way to draw a ring. We can do that by creating a custom shape. This shape consists of a circle, this will be our background, and on top of that an arc whose length is determined by the progress. Although there's no built-in arc shape, we can use the trim method to create one from a circle. And how do we achieve the rounded ends of our arc? Well, that's just a matter of setting the stroke style's line cap property to round. And the final ring progress bar will consist of 3 concentric rings. The size and the overall line width of the rings should both be adjustable. The progress and the color of each ring should also be configurable. Finally, we'll need a way to animate the progress of our ring progress bar. There are different ways to do that, so you can be creative and choose the approach that you think works best. Now that we know what our final ring progress bar will look like and what it will need, let's get started. I'll let you take it from here. Pause the video and see if you can build the ring progress bar on your own. When you're done, come back and we'll go over my solution. Good luck! Welcome back! Let's take a look at my solution to the ring progress bar challenge. I've gone ahead and created a playground project. I could have also done this in a SwiftUI app, but this way I can show you how to display SwiftUI views in a playground. I'll create a SwiftUI view, so I'm gonna import SwiftUI at the top. I'll also rely on the live view feature of playgrounds, so I'll need to import playground support. Now that we have our imports in place, let's start by creating a custom view that will represent a ring progress bar. I'll call this structure progress ring, which conforms to the view protocol. To adopt the view protocol, I'll add a body property of type someView. This is where I'll put all the code to draw the progress ring. Let's start by adding a circle view. This will be the background of the ring. I'll use the stroke modifier and I'll set the line width to, say, 30. Let's set the foreground color to red so we can see it easily. And I'll set a frame to constrain the size of this circle. 200 by 200 seems like a good size. There are no errors when I build this code, but there's also no visible output. That's because our circle view is not being displayed in the live view. To display it, I'll set the playground page's current live view to an instance of our progress ring structure. Okay, now we can see our circle. I'll set the default padding so the circle is not cropped by the live view. Great, now let's add an arc on top of that circle. I'll copy this circle view and I'll paste it below. I'm gonna change its foreground color to green so that it stands out from the background circle. Then I'm gonna use the trim method to create an arc from this circle. The start fraction should be 0, since I want to start drawing the arc from its beginning. And for the end fraction, I'll enter 0.5 for now to draw half of the arc. If I run this code, we can see that the arc is being drawn below the red circle rather than on top of it. That's because the green circle is being added after the red one, and SwiftUI renders views in order. To fix that, I'll add a Z-stack and place both of my circle views inside it. This will allow us to place multiple views on top of each other. I'm gonna select these lines and I use the Ctrl-I keyboard shortcut to indent the code. We can now take a look at the result. This looks promising, but the arc starts at 3 o'clock rather than at the top like we wanted. I'll use the rotation effect modifier and rotate the view by -90 degrees. If I run the code again, we can see that the arc is now in the correct position. Now let's have a look at the ring progress on the Apple Watch. As you can see, the background circle's color is a darker shade of the arc's color. To recreate this, I'm gonna set the background circle's opacity to 0.3. And I'll set the second circle's foreground color to red as well. The result looks good. The foreground circle is the same color as the ring and the arc is drawn on top of it. However, the arc's ends are not rounded like they are on the Apple Watch. There's an easy fix for that. Setting stroke style's line cap property to round will do the trick. So I'll update the stroke modifier and set the style to stroke style with line width 30 and line cap round. If I run the code, we can see that the arc now has rounded ends. The next step is to clean up the code a bit. I'll get rid of the padding from the circle views and add it to the Z-stack instead. Then I'll extract the ugly hard-coded values and make them configurable. Let's start with the colors. I'll add a property to our progress ring structure for the foreground color, of type color. And I'll replace each occurrence of red with foreground color. Next, I'll extract the line width and the progress. Let's remove the corresponding hard-coded values from the code and use our new properties instead. Last but not least, I'll add a property for the frame size. And I'll use it as the width and height of our frame. I'll need to update the initializer to set the new properties. So progress ring of size 200, line width 30, progress 0.5 and foreground color red. And I can now use different colors or line widths without having to mess with the progress ring's code. But that's only one progress ring. We need 3 of them to recreate the Apple Watch's activity rings. I'll start by creating a new view that will hold our 3 progress ring instances. I'll call it rings and I'll add the body property with a Z-stack. As you might recall, a Z-stack lets us lay out its child views on top of each other. And I'll add 3 progress ring instances using burnt-in values for now. Progress ring of size 200, line width 30, progress 0.5, foreground color, say red. The second one of size 140, line width 30, progress 0.3, and foreground color green. And the last one, progress ring of size 80, line width 30, progress 0.2, and foreground color, say cyan. The line width is 30, and I adjusted the frame sizes so that the circles are concentric. And let's not forget to set the live view to a rings instance. If I run the code, we get a pretty good looking replica of the Apple Watch's activity rings. But I'm not happy with the hard-coded values. I want to be able to create different ring sizes without having to edit the code. So I'll add a property to the ring structure for the size, line width, the 3 progress values, and the ring colors. I'll name them so that it's clear what each value represents, and I'll also set some default values. I want my rings to update automatically whenever I make changes to the progress properties, so I'll mark them as binding properties. And since these are binding properties, I'll have to access them using the $prefix. So let's make the necessary changes. I'll need to turn the progress string's progress into a binding property as well. Finally, I'll go ahead and create a new view called Preview. It wraps a rings instance and a button in a VStack, which renders UI elements vertically. I'll use the 3 state properties for the progress values which get initialized to 0. These properties get updated to random values whenever we hit the button. I used the random method of the CGFloat type to generate random values in the range 0, 1. We can now update the rings by hitting the button. Pretty cool, huh? The only thing that's missing is the animation. I'll go back to the progress string structure and I'll add an animation modifier. So whenever the value of the progress property gets updated, the animation will automatically run. I used an easy note animation style, but you can use any style you like. And that's it. We now have a fully functioning animated replica of the Apple Watch's activity rings. Stay tuned for more Friday Swift Code challenges. Welcome to another Friday Swift Code challenge. Today I'm gonna show you the fast and slow pointer technique, also known as the Tortoise and Hare algorithm. Linked lists are commonly used data structures in Swift. A linked list is basically a chain of special elements called nodes. A node holds a value and 1 or 2 references depending on the type of the list. If we have a list with 2 references, it's called a doubly linked list. Doubly linked lists have references to both the next and the previous nodes. If we have a list with nodes that only have a reference to the next node, that's called a singly linked list or unidirectional list. In this challenge, your task is to write a function that takes a singly linked list as its input parameter and returns the node at the middle of the list. Consider the following linked list. The middle node in this list would be node 2. If the linked list has an even number of nodes, we'll return the node closer to the end of the list. So for a list with 4 nodes, we'd return node 3, since it's one of the 2 middle nodes in the list and the one closer to the end. Note that linked lists are not built into the Swift standard library. Thus, we'll use a custom singly linked list implementation for this challenge. You can download the Starter Playground project from GitHub. I've included the link in the description. So here's the node class that we'll use to create our linked list. It's a generic class. Thus, it can hold any type of value. The node class has 2 generic properties, value and an optional next property. The next property holds the reference to the next node in the list. The linked list class relies on the node class to create a singly linked list. The first node is called the head, and the last node is called the tail. The class also has 2 corresponding computed properties, head and tail, for retrieving the first and last nodes in the list. Both head and tail are of type node and are optional, meaning they can be nil. Thus, an empty list will have both head and tail set to nil. Note that first and last are internal properties. I've only exposed the getters via the head and tail computed properties to avoid directly setting the first or the last node. We don't want that. We'll use the append method to add new nodes to the end of the list. The append method creates a new node first. Then it checks if the linked list is empty by looking at the tail node. If the list is not empty, the new node is appended to the end of the list by setting the current tail node's next property to point to the new node. On the other hand, if the list is empty, the first node is set to point to the new node. Finally, the last node is set to point to the new node in both cases. To create a new list, you simply invoke the initializer. At this point, the list is empty, and both head and tail are nil. We'll call the append method to add a few nodes. List append 1, list append 2, and list append 3. You can use the head and tail properties to access the corresponding nodes in the list. List.head.value should print 1, and list.tail.value should print the value of the last node, which is 3. And the next node in the linked list can be retrieved using the next property of a node. For instance, to get the second node in the list, I'll write list.head.next.value. Okay, that's enough background information. Time to write some code. As usual, I let you work on this challenge before I show you my solution. Use the playground file linked in the description as a starting point. Now press pause and code away. When you're ready, hit play and take a look at my solution. And we're back. How did you do? Now let's have a look at my solution. The easiest way to solve this problem is to use the fast and slow technique. I'll start by creating a linked list extension to demonstrate a useful feature of the Swift language that lets us extend existing types without modifying their source code. Then I'll create a computed property called middle. It's a generic property of type node, and I'll make it optional in case the list is empty. This property should be read-only. I can specify that by providing only the getter. First, I'll check if the list is empty. If it is, I'll return nil. I'll set up two variables called slowPointer and fastPointer, and initialize both to point to the head of the linked list. Then I'll write a while loop that will run until the fastPointer or its next node reaches the end of the list. You'll understand why we need the next node check in just a moment. Now here comes the clever part. Inside the while loop, I advance the slowPointer by one node and the fastPointer by two nodes at a time. That's why this technique is called fast and slow. I'll keep moving the pointers through the list as long as the fastPointer and the fastPointer's next property is a nil. When the fastPointer reaches the end of the list, the slowPointer is at the middle of the list, because it moved through the list at half the speed of the fastPointer. The following animation shows how this works. Now that I have the node at the middle of the list, I can return it. And that's pretty much it. All that's left to do is test our code to make sure it works. So let's print the value of the middle node in our sample list. If it's nil, I'll print list is empty. Prints 2. Okay, how about an even numbered list? I'll append another node to our list with a value of 4. List.append 4. The result should be 3. And prints 3. Great! I hope you enjoyed this challenge and that you learned something new. Don't forget to like and subscribe if you want to see more Swift code challenges like this in the future. And if you want to delve a bit deeper into the Swift programming language, then check out my course on data structures and algorithms in Swift. It's available using the link in the description below. Thanks for watching, and I'll see you next time.